There is a question that has kept astronomers awake at night, that has haunted philosophers for centuries, that has quietly sat at the back of every human mind who has ever stepped outside on a clear night and looked upward into the dark and felt something enormous and wordless pressing down on their chest. The question is deceptively simple. It is only 11 words long. But those 11 words contain the weight of 4.5 billion years of cosmic history, of violent collisions and silent drifts, of fire and ice and chemistry so delicate it borders on the miraculous. The question is this: do we live in the most perfect solar system ever? Now, before you answer that too quickly, before you allow your familiarity with this solar system to make you dismiss it as ordinary, I want you to do something. I want you to take everything you think you know about space and set it aside for a moment. Not permanently, just for the duration of this conversation. Because what we are about to go through together is not a story you have been properly told before. Not in this depth, not with this level of detail, not with the full weight of what modern science actually tells us about where we live and what it means that we are here at all. Right now, as you are reading or listening, you are sitting on a rocky planet that is hurtling through space at approximately 29.78 kilometers per second. That is 107,000 kilometers per hour. You are orbiting a star that is itself moving through a galaxy at around 220 kilometers per second. That galaxy is moving through the local group of galaxies. The local group is moving through the larger supercluster, and all of that, every galaxy, every star, every atom of hydrogen drifting in the void, is racing outward through an expanding universe that is approximately 93 billion light-years across in the observable portion alone. You are not standing still. You have never stood still. Not for a single second of your entire life. And yet, somehow in the middle of all of that violent, turbulent, radiation-drenched, chaotic enormity of the cosmos, you are sitting here reading this. You are alive. You are comfortable enough to think abstract thoughts. You can breathe. You can drink water. The temperature outside your window, wherever you are on Earth, is probably somewhere within a range that your body can manage. You are not frozen. You are not boiling. You are not being torn apart by gravitational tides or blasted to oblivion by the relentless radiation of a nearby massive star. You are just here. Quietly, Redding. That should terrify you a little. Not in a bad way. In the best possible way. Because when you truly understand the cosmic context of your existence, the sheer number of things that had to go exactly right for this moment to happen, you begin to realize that the universe around you is not the background to your story. It is the story. And we are only just beginning to understand how extraordinary that story really is. Let us begin at the very beginning. Not the beginning of human civilization, not the beginning of life, but the actual beginning of everything that made this solar system possible. We have to go back approximately 4.6 billion years to a time when there was no sun, no Earth, no moon, no planets, nothing but a vast, cold, slowly rotating cloud of gas and dust drifting in one of the outer spiral arms of the Milky Way galaxy. This cloud was mostly hydrogen and helium, the two most abundant elements in the universe, but it also contained tiny traces of heavier elements: carbon, oxygen, iron, silicon, nitrogen. These were the ashes of older stars that had lived their lives, burned through their fuel, and died in spectacular explosions called supernovae, scattering their contents across the surrounding space. Our solar system is, in a very literal sense, made of dead stars. Every atom of iron in your blood was forged in the core of a star that died before our sun was born. You are, as Carl Sagan so beautifully put it, made of star stuff. Now this molecular cloud, this vast, cold nursery of cosmic material, began to collapse under its own gravity. Something disturbed it. Scientists believe it may have been a nearby supernova sending a shockwave through the cloud, compressing it enough to trigger gravitational collapse. Or it may have been a simple density fluctuation, a slight unevenness in the cloud that caused one region to pull slightly harder than its surroundings, drawing more material in, increasing its gravity, drawing in even more material in a runaway process. Whatever the trigger, once the collapse began, it accelerated. As the cloud collapsed, it did something crucial. It began to spin. This is because of a law of physics called conservation of angular momentum. When a large, slowly rotating mass collapses into a smaller volume, it must spin faster to conserve its angular momentum, the same way a figure skater pulls in their arms to spin faster. As the collapsing cloud spun faster, it flattened into a disk shape, a protoplanetary disk with a dense, hot central concentration that would eventually become our Sun. The outer regions of this disk were where the planets would eventually form, and the story of how they formed and where they ended up is one of the most extraordinary and consequential stories in the history of this solar system. In the center of the collapsing cloud, material was piling up at an incredible rate. The temperature and pressure at the core were rising to unimaginable levels. After a few tens of millions of years, the temperature at the center reached approximately 10 million degrees Celsius. At that point, something historic happened. Hydrogen atoms, stripped of their electrons by the extreme conditions, began fusing together to form helium. Nuclear fusion had ignited. A star was born. Our Sun switched on approximately 4.603 billion years ago, and when it did, it released a powerful stream of charged particles called the solar wind that blew outward through the disk, sweeping away much of the remaining gas and dust, leaving behind the rocky and icy material that would coalesce into the planets we know today. But here is where the first twist in this story appears. The way the planets formed, where they ended up, and what roles they play relative to each other is not some random accident. There is an architecture to our solar system that, when you examine it closely, begins to look like something extraordinary. And I do not use that word lightly. The observable universe contains somewhere between 1 and 2 trillion galaxies. Our own Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Of those stars, the overwhelming majority are not like our Sun. This is a fact that does not get mentioned often enough. Most stars in the Milky Way are red dwarfs, also known as M-type stars. These small, dim, cool stars make up approximately 70 to 73% of all stars in our galaxy. They burn their fuel so slowly that some of them will still be burning long after the universe has aged to 100 times its current age. They sound ideal. They are everywhere, they are long-lived, and many of them have planets. But here is the problem with red dwarf stars, and it is a very big problem. They are extraordinarily violent in their youth and remain magnetically active for far longer than Sun-like stars. Red dwarfs produce enormous flares, eruptions of X-ray and ultraviolet radiation that can be hundreds of times more powerful than anything our Sun produces. Because planets around red dwarfs need to be very close to the star to receive enough warmth for liquid water, those planets are exposed to this intense radiation at point-blank range. Research has shown that the habitable zone around a red dwarf star is so close that planets there experience radiation environments that are 10 to 100 times more intense than what Earth receives. This radiation can strip away planetary atmospheres, damage or destroy the complex molecules necessary for life, and cause mass extinction events on geological timescales with a regularity that would make sustained complex life essentially impossible. But the red dwarf problem goes deeper than just radiation. Planets in the habitable zones of red dwarf stars are so close to their host stars that they experience extreme gravitational tidal forces. These tidal forces can, over time, cause a phenomenon called tidal locking. A tidally locked planet rotates exactly once per orbit, which means one side permanently faces the star and the other side permanently faces away. The day side becomes an inferno, the night side becomes a frozen wasteland. The terminator line, the thin zone between the two hemispheres, might theoretically have tolerable temperatures, but the atmospheric dynamics of such a planet would be extremely complex and likely inhospitable. There would be permanent hurricane force winds as the hot day side atmosphere rushed toward the cold night side. It would be a world of extremes, not the gentle, temperate, seasonally varied environment that complex life requires. Now consider the next most common type of star. After red dwarfs, the next most common are orange dwarf stars, or K-type stars, which make up about 13% of stars. They are larger and brighter than red dwarfs, and their habitable zones are a bit farther out, which means the tidal locking problem is less severe and the radiation issue is more manageable. Some scientists actually argue that K-type stars may be the best candidates for life because they are long-lived and relatively stable. But here is something interesting. Our Sun is not a K-type star. Our Sun is a G-type star, a yellow dwarf, and according to NASA, Sun-like G-type stars make up only about 6% of all stars in the Milky Way. Only 6%. Among the hundreds of billions of stars in our galaxy, only a small fraction are genuinely similar to our Sun. And what makes the Sun special among its peers? The Sun is classified as a G2V star, placing it toward the hotter end of the G-type range, but well within the zone of stability. The Sun's luminosity, the total energy output, varies by less than 0.1% over multi-decade periods. This extraordinary stability is crucial. Stars that vary significantly in their output create dramatic fluctuations in the radiation received by orbiting planets, which would destabilize climates, erode atmospheres, and make sustained complex life impossible. Our Sun maintains what astronomers call a remarkably steady energy output, providing the long-term consistency that billions of years of biological evolution require. But the Sun's stability is only one part of what makes it exceptional. The Sun's age matters enormously. At approximately 4.6 billion years old, the Sun is roughly at the halfway point of its main sequence life. Main sequence is the term astronomers use for the long, stable burning phase of a star's life when it is fusing hydrogen into helium in its core. The Sun will remain on the main sequence for another approximately 5 billion years. This means it has already provided 4.6 billion years of stable energy output for the solar system and has another 5 billion years of stability remaining. This extraordinary lifespan creates the vast temporal canvas on which evolution can paint its masterpiece. Life on Earth needed hundreds of millions of years just to get from simple single-celled organisms to multicellular life. It needed the full sweep of geological time to produce the complexity we see today. Only a star like the Sun, with its billions of years long stable burning phase, can provide that kind of patient, consistent energy over the timescales that complex life demands. The Sun's position within the Milky Way also deserves attention. Our solar system is located approximately 26,000 light-years from the galactic center, in a relatively quiet region between two major spiral arms in what is called the Orion Arm or local arm. This position is significant for several reasons. The center of the Milky Way is an extraordinarily hostile environment. It contains a supermassive black hole called Sagittarius A, with a mass of approximately 4 million solar masses. The central regions of the galaxy are densely packed with stars, leading to frequent supernovae, intense X-ray and gamma-ray radiation, and gravitational perturbations that would routinely disrupt planetary orbits. Life as we know it could not survive in the galactic center. In 2004, astrophysicist Charles Lineweaver and his colleagues published a landmark paper introducing the concept of the Galactic Habitable Zone, or GHZ. This is the region of the galaxy where conditions are most conducive to the formation and survival of complex life. The GHZ excludes the dangerous galactic center. It also excludes the outer edges of the galaxy, where stars were formed from primordial gas that was too poor in heavy elements to build rocky planets. The GHZ is a roughly annular region, a ring-shaped zone, in the middle portions of the galaxy where star density is moderate, heavy element abundance is sufficient, and radiation hazards are manageable. Our solar system sits squarely within this zone, not close to the edge, not bordering the danger zone, right in the middle of the region that maximizes the probability of long-term habitability. Furthermore, our Sun's orbit around the galactic center is remarkably circular. Most stars in the galaxy have elliptical orbits that carry them through regions of varying stellar density and radiation levels. Our Sun's orbit stays within a relatively narrow range of galactocentric distance, keeping us consistently within the galactic habitable zone throughout the Sun's journey around the galaxy. The Sun also orbits at nearly the same speed as the galaxy's spiral arms rotate, which means it rarely crosses through a spiral arm. Spiral arms are regions of elevated stellar density and therefore elevated supernova frequency. By staying between the arms, our solar system avoids these periodic radiation bombardments that might otherwise reset the biological clock of any evolving life. Now we have talked about where we are in the galaxy and what kind of star we orbit. But the next layer of this story, the planetary architecture of our solar system itself, is where things get truly remarkable. Because when you compare our solar system's structure to the thousands of other planetary systems we have discovered, the differences are striking and important. The first exoplanets were confirmed in the early 1990s. As telescopes like the Kepler Space Telescope, launched in 2009, began cataloguing planets around other stars, scientists expected to find solar systems that looked roughly like ours. Rocky planets in the inner system, gas giants farther out, a reasonable arrangement. What they found instead was something completely different and deeply surprising. The vast majority of planetary systems discovered look nothing like ours. The dominant architecture of planetary systems across the galaxy appears to be what astronomers call compact multi-planet systems, where multiple planets of various sizes, often including so-called super-Earths, pack closely together within what would correspond to Mercury's orbit around our Sun. These systems are dramatically different from ours, and the differences have profound implications for habitability. One of the most common features found in exoplanet surveys was the presence of what astronomers call hot Jupiters. These are gas giant planets roughly the size of Jupiter or larger, but orbiting incredibly close to their host stars, often completing a full orbit in just a few days. In our solar system, Jupiter sits at 5.2 AU, meaning 5.2 times the Earth-Sun distance. It is cold, distant, and gravitationally dominant over the outer solar system. Hot Jupiters orbit their stars at distances of 0.05 AU or less. The presence of a hot Jupiter in a system has catastrophic implications for any inner rocky planets. As gas giants form and migrate inward toward the star in the early history of a planetary system, they gravitationally sweep through the inner solar system like a cosmic wrecking ball, ejecting or consuming rocky planets and disrupting the stable orbital architecture that life requires. Systems with hot Jupiters are generally considered hostile to Earth-like habitable worlds. In our solar system, Jupiter did not migrate inward. It formed at about its current distance, and, after some complex gravitational interactions with Saturn in the early solar system, settled into its current stable orbit. This is extraordinary. It means that the inner solar system was left largely undisturbed, allowing the rocky planets, including Earth, to form and evolve in peace. Jupiter's story in our solar system is one of the most important and underappreciated stories in the entire history of our planet. Jupiter is the largest planet in our solar system, with a mass of approximately 318 times that of Earth. Its gravitational influence is felt throughout the entire solar system. Beyond its role in the early solar system as a planetary bodyguard that did not destroy the inner system, Jupiter plays an ongoing protective role that becomes vivid when you consider actual documented events. In July 1994, the world watched in astonishment as comet Shoemaker Levy 9, a comet that had been broken into 21 large fragments by Jupiter's tidal forces on a previous close approach, came raining down into Jupiter's southern hemisphere over the course of a week, from July 16 to July 22. The impacts were cataclysmic. Individual fragments released energy estimated to be thousands of times greater than the entire nuclear arsenal of Earth. The impacts left dark scars in Jupiter's atmosphere larger than the planet Earth itself, scars that were visible for months. This event was not just a spectacular astronomical show. It was a demonstration, a real, documented, empirical demonstration of exactly how Jupiter functions as a gravitational trap for large cometary bodies that might otherwise have continued inward through the solar system, potentially threatening the inner planets. The comet had been gravitationally captured by Jupiter and ultimately destroyed by Jupiter, a sequence of events that illustrates the role Jupiter plays in clearing dangerous objects from the inner solar system. Research by astrophysicist Kevin Grazier at NASA's Jet Propulsion Laboratory has used computer simulations to study what the impact rate on Earth would be in the absence of Jupiter. His work suggests that without Jupiter, Earth would experience a significantly higher rate of large impacts, potentially by an order of magnitude or more over geological timescales, which would have profound consequences for the continuity of complex life. While the precise number remains a topic of ongoing research and some debate, the consensus is that Jupiter's gravitational presence fundamentally alters the dynamics of the inner solar system in ways that are broadly protective. However, here is where the story of Jupiter gets more nuanced and more interesting, because the scientific truth is never as simple as the popular version. Jupiter's protection is not absolute and not entirely one-directional. Jupiter's gravity can also disturb asteroids in the main asteroid belt, sending some of them on trajectories that intersect with the inner solar system. The asteroid belt, which lies between Mars and Jupiter at distances of roughly 2.2 to 3.2 AU from the Sun, is itself a product of Jupiter's gravitational influence. Early in the solar system's history, the material in the asteroid belt region could have accreted into a full-sized planet, but Jupiter's gravitational perturbations prevented this, keeping the belt as a collection of rocky and metallic bodies rather than allowing them to coalesce. This means Jupiter both protects Earth from some projectiles and is responsible for the existence of the main threat that sends asteroids toward Earth in the first place. The relationship is complex, not simple, and that complexity is one of the things that makes our solar system so fascinating and so unlike what a naive intuition would predict. Saturn plays its own critical role in the gravitational ecology of the solar system. With a mass of approximately 95 times that of Earth, Saturn is the second largest planet and works in gravitational concert with Jupiter to shape the orbits of objects in the outer solar system. The interaction between Jupiter and Saturn is described by what planetary scientists call their orbital resonance, and the ratio of their orbital periods, approximately 2:5, creates a gravitational dynamic that helps stabilize the overall architecture of the outer solar system. Research by Alessandro Morbidelli and colleagues on the NICE model of solar system evolution has shown that the gravitational interplay between Jupiter and Saturn was responsible for redirecting objects from the outer solar system inward during what is called the Late Heavy Bombardment, a period of intense asteroid and comet impacts that occurred approximately 4.1 to 3.8 billion years ago. This bombardment, while violent, is now believed to have delivered crucial ingredients to the inner solar system, including water and organic molecules that may have been essential precursors to life. The asteroid belt itself, despite its reputation as a dense and dangerous field of rocky bodies, is actually far emptier than its popular portrayal suggests. If you were somehow transported to the asteroid belt, you would be enormously unlikely to see another asteroid with the naked eye. The asteroids are spread across a volume of space so vast that the average distance between them is hundreds of thousands of kilometers. The dramatic asteroid field depicted in science fiction films, with objects packed densely enough to require constant dodging, is almost entirely fictional. The real asteroid belt is mostly empty space, with its total mass being only about 4% of the mass of the Moon, and more than half of that mass concentrated in just the four largest objects: Ceres, Vesta, Pallas, and Hygeia. This relative emptiness is itself a product of Jupiter's gravitational stirring, which prevented the belt from accreting into a larger body, and also gradually depleted it over billions of years. Uranus and Neptune, the ice giants of the outer solar system, occupy orbits at 19.2 and 30.1 AU respectively. Their position in the outer solar system helps define the outer gravitational boundary of our planetary system. and interacts with the Kuiper belt, the region of icy bodies that extends from approximately 30 to 50 AU. Neptune's gravitational influence shepherds the Kuiper belt, preventing it from sending a constant rain of comets into the inner solar system. The presence of these outer giants, therefore, is part of a layered gravitational defense system, with Neptune and Uranus managing the outer icy bodies and Jupiter and Saturn managing the middle and inner zones. This arrangement is not found in most known exoplanet systems. Now we come to the extraordinary specifics of Earth's position within this solar system, and this is where the story becomes deeply personal, because we are talking about the precise circumstances that created the very ground beneath your feet. Earth orbits the Sun at a distance of approximately 149.6 million kilometers, a distance that astronomers have defined as 1 astronomical unit, or 1 AU. The habitable zone of our Sun, the range of orbital distances at which a planet could theoretically maintain liquid water on its surface, extends from approximately 0.95 AU to about 1.37 AU under most scientific models. Earth sits at 1.0 AU. It does not merely sit within the habitable zone, it sits almost exactly in the middle of the more conservative calculations for that zone. But consider the precision of this. Venus orbits at 0.72 AU, placing it deep inside the inner boundary of the habitable zone. Venus has a surface temperature of approximately 465 degrees Celsius, hot enough to melt lead. It has a crushing atmospheric pressure 92 times that of Earth, an atmosphere of mostly carbon dioxide with clouds of sulfuric acid. It experiences a runaway greenhouse effect that has made it the most hellish environment in the known solar system. Mars, on the other hand, orbits at 1.52 AU, just outside the outer boundary of the habitable zone. Mars has an average surface temperature of -60 degrees Celsius. It has a thin atmosphere with a pressure of less than 1% of Earth's. Its surface is barren, frozen and bombarded by ultraviolet radiation because it lacks both a substantial atmosphere and a global magnetic field. Between the Venusian hell at 0.72 AU and the Martian freeze at 1.52 AU, Earth occupies the extraordinary middle ground at 1.0 AU, which works out to just right in a way that is not coincidental, but is the product of specific conditions that took billions of years to create and maintain. Earth's orbital eccentricity, which is the measure of how elliptical or circular the orbit is 0.0167. A perfectly circular orbit would have an eccentricity of 0. Earth's eccentricity of 0.0167 means the orbit is very nearly circular, with the maximum variation in Earth's distance from the Sun being only about 3% over the course of a year. This low eccentricity is enormously important for climate stability. The more elliptical an orbit, the greater the variation in solar energy received at different points in the orbit, and therefore the greater the seasonal extremes. Earth's nearly circular orbit ensures that the variation in solar energy received throughout the year is very small, contributing to the relatively moderate global climate that complex life requires. Compare this to Mars, which has an eccentricity of 0.093, approximately 6 times more elliptical than Earth, and you can understand one of the additional factors that makes Mars's climate more extreme and less hospitable. Earth's axial tilt of 23.5 degrees is another extraordinarily well-tuned parameter. The axial tilt or obliquity determines how much seasonal variation a planet experiences. If the tilt was 0, there would be no seasons. The poles would be perpetually cold and dark, the equator perpetually hot, and the distribution of habitable latitudes would be very narrow. If the tilt were very large, say 90 degrees like the planet Uranus, the poles would point directly at the Sun for half the year and directly away for the other half, creating catastrophic seasonal extremes that would freeze and then boil regions of the planet on alternating timescales. Earth's 23.5 degree tilt creates mild, regular seasons that distribute solar energy across a wide range of latitudes over the course of a year, allowing a much larger portion of Earth's surface to be hospitable to life. The tilt is also the reason for biodiversity patterns that vary with latitude and season, creating the variety of ecological niches that drove evolutionary diversification. But here is the twist. Earth's axial tilt does not stay perfectly fixed at 23.5 degrees. Over periods of about 41,000 years, Earth's obliquity cycles between approximately 22.1 and 24.5 degrees, a variation of about 2.4 degrees. This cycle is one of the Milankovitch cycles, named after Serbian mathematician Milutin Milankovic, who in the early 20th century mathematically described how small, periodic variations in Earth's orbital parameters drive long-term climate cycles, including ice ages. The variation in Earth's obliquity contributes to the timing and intensity of ice age cycles, which have had profound effects on the evolution of life on Earth, including the evolution of our own genus Homo. The remarkable thing is that this variation of 2.4 degrees is extraordinarily small. By comparison, Mars's axial tilt varies wildly over millions of years, swinging between approximately 10 and 60 degrees in chaotic fashion. This extreme variation would produce climate swings on Mars far more dramatic than any ice age in Earth's history. The reason Earth's tilt is so stable compared to Mars is because of a single extraordinary feature of our planet: the Moon. Our Moon is the most underappreciated object in the solar system when it comes to understanding why life exists on Earth. The Moon is so familiar, so constant in our night sky, that we take its presence for granted. But the Moon is extraordinary in ways that are only beginning to be fully appreciated. The most immediately striking thing about the Moon is its size relative to Earth. The Moon has a diameter of about 3,474 kilometers, which is about 27% of Earth's diameter. This makes it by far the largest satellite relative to its host planet among the rocky planets of the solar system. Mars has two tiny moons, Phobos and Deimos, which are essentially captured asteroids measuring only about 22 and 12 kilometers across. Mercury and Venus have no moons at all. Our Moon is not just large, it is disproportionately, almost ridiculously large for a moon of a rocky inner planet. The explanation for the Moon's existence is one of the most dramatic events in our solar system's history. Approximately 5 billion years ago, shortly after Earth had formed and while it was still in a partially molten state, a roughly Mars-sized body that planetary scientists have named Theia collided with the proto-Earth in a glancing blow of unimaginable violence. The impact was so energetic that it vaporized much of Theia and a large portion of Earth's outer layers, sending an enormous plume of vaporized rock and metal into orbit around Earth. Over the following months and years, this debris coalesced under gravity into the Moon. This hypothesis, known as the giant impact hypothesis, is supported by extensive evidence, including the chemical and isotopic composition of moon rocks returned by the Apollo missions, which show a composition remarkably similar to Earth's mantle, and the Moon's lack of a substantial iron core, consistent with the idea that it formed primarily from mantle material rather than from material from Theia's metallic core. The Moon that formed from this catastrophic collision was initially much closer to Earth than it is today, perhaps just 20,000 to 30,000 kilometers away, compared to its current average distance of about 384,400 kilometers. At that distance, it would have appeared enormous in the ancient sky, and its tidal forces on Earth were correspondingly much stronger. Over the approximately 4.5 billion years since its formation, the Moon has been slowly receding from Earth at a rate of about 3.8 centimeters per year, a consequence of the tidal interaction between the Moon and Earth, in which Earth's rotation is gradually slowing and the Moon is gradually moving to a higher orbit. The stabilizing effect of the Moon on Earth's axial tilt has been the subject of significant scientific research. A landmark 1993 paper by Jacques Lascar and colleagues calculated that without the Moon, Earth's obliquity could vary chaotically between approximately 0 and 85 degrees over tens of millions of years. A variation of that magnitude would be catastrophic for the continuity of complex life. The dramatic shifts in how solar energy was distributed across Earth's surface would produce climate changes far more extreme than any that complex organisms could easily adapt to. The Moon's gravitational torque on Earth's equatorial bulge, the slight extra material around Earth's equator caused by its rotation, provides the stabilizing influence that keeps Earth's obliquity in its relatively narrow range. It is worth noting that subsequent research, including a 2013 paper by Jason Barnes and colleagues, has suggested the picture is somewhat more nuanced, and that a moonless Earth might not be quite as chaotically unstable as Lasker's early calculations suggested. Nevertheless, the consensus view is that the Moon's presence provides a meaningful stabilizing influence on Earth's rotational dynamics, contributing to the long-term climate stability that complex life requires. The Moon's tidal forces have played other critical roles in Earth's biological history. The tides created by the Moon's gravity have throughout Earth's history created an intertidal zone, the region of coastline between the high and low tide marks, that is periodically wet and periodically dry. Many scientists believe that this zone was crucial in the origin of life, providing an environment where organic molecules could be concentrated and diversified through cycles of wetting and drying. The tidal mixing of the oceans also helps regulate oceanic chemistry, distributing nutrients and oxygen throughout the water column. On a geological timescale, tidal forces have shaped the evolution of many ocean species and have been linked to the emergence of life from the oceans onto land, as organisms in the tidal zone were periodically exposed to air and were under evolutionary pressure to develop adaptations for surviving these exposures. The Moon also gives us something that seems superficially trivial but is scientifically profound. When the Moon moves directly between the Earth and the Sun during a total solar eclipse, it blocks out the Sun's disk almost perfectly. Not partially, not by a huge margin, almost exactly. The Sun is approximately 400 times larger in diameter than the Moon, but it is also approximately 400 times farther from Earth. These two factors cancel out, making the Moon appear almost exactly the same size as the Sun in the sky. The result is the total solar eclipse, one of the most awe-inspiring phenomena in nature, in which the Sun's corona, its outer atmosphere, becomes briefly visible. This cosmic coincidence has enabled some of the most important scientific observations in history. The 1919 solar eclipse was used to confirm Einstein's general theory of relativity by measuring the bending of starlight around the Sun's mass. The study of the solar corona during eclipses has revealed fundamental information about solar physics. It is, of course, just geometry, but the geometry is extraordinary, and it highlights the fact that our Moon and Sun are in a very precise physical relationship. Now let us go deeper into Earth itself, because the planet's interior and its geological activity are just as crucial to the story of life as its external conditions. Earth is the only known planet with active plate tectonics. This is a fact of staggering significance. Plate tectonics is the system by which Earth's outer layer, the lithosphere, is divided into roughly 15 major plates that move relative to each other at speeds of typically 2 to 10 centimeters per year. Where plates collide, mountains are built. Where they diverge, new ocean floor is created. Where one plate slides under another in a process called subduction, oceanic crust dives back into the mantle to be melted and eventually recycled back to the surface through volcanic activity. This system is not merely a geological curiosity, it is the engine of long-term planetary habitability. The most critical function of plate tectonics for habitability is its role in the carbonate-silicate cycle, which is Earth's long-term carbon thermostat. Carbon dioxide in the atmosphere combines with rainwater to form carbonic acid, a weak acid that chemically weathers silicate rocks at the surface, releasing calcium and magnesium ions. These ions are washed into the oceans by rivers, where they combine with carbonate ions and are deposited as calcium carbonate, otherwise known as limestone, on the ocean floor. This process effectively removes carbon dioxide from the atmosphere and stores it in the rock. Without a mechanism to return this carbon dioxide to the atmosphere, Earth would gradually cool and eventually freeze as the atmospheric carbon dioxide was progressively sequestered in carbonate rocks. Plate tectonics provides the return mechanism. When oceanic crust loaded with carbonate sediments is subducted beneath a continental plate, the heat and pressure in the mantle decompose the carbonate rocks, releasing carbon dioxide, which is then vented back into the atmosphere through volcanoes. This creates a negative feedback loop that regulates Earth's atmospheric carbon dioxide concentration, and therefore its global temperature over geological timescales. When the climate is warm, silicate weathering is enhanced, drawing down more carbon dioxide and cooling the planet. When the climate is cold, weathering rates decrease, carbon dioxide builds up from volcanic outgassing, and the planet warms. This self-regulating system has maintained Earth's surface temperatures within the range necessary for liquid water for billions of years, even as the sun's luminosity has increased by approximately 30% over the history of the solar system. This is a remarkable point that deserves to be emphasized. When the solar system formed 4.6 billion years ago, the sun was significantly less luminous than it is today, approximately 70% of its current brightness. By standard calculations, an Earth with its current atmospheric composition should have been completely frozen 4 billion years ago. But the geological and fossil evidence clearly shows that liquid water existed on Earth's surface at least 3.8 billion years ago. This paradox, known as the faint young sun paradox, is resolved by the carbonate-silicate cycle operating through plate tectonics. In the early Earth with a dimmer sun, silicate weathering would have been reduced, allowing volcanic carbon dioxide to build up in the atmosphere. The enhanced greenhouse effect would have kept the planet warm enough for liquid water. As the sun gradually brightened over billions of years, the increased warmth enhanced weathering, drawing down the excess carbon dioxide and keeping temperatures in check. Earth's geology and its atmosphere have been in a dynamic conversation for billions of years, adjusting to the slowly brightening sun to maintain a habitable climate. This is an extraordinary system. Compare Earth's situation to Venus and Mars. Venus has no active plate tectonics, or at least not in the same global style as Earth. Without the subduction of carbon-rich ocean floor and the recycling of carbon through the carbonate-silicate cycle, Venus has accumulated an atmosphere that is 96.5% carbon dioxide, creating a runaway greenhouse effect that has raised surface temperatures to the aforementioned 465 degrees Celsius. Venus may once have had liquid water on its surface, perhaps billions of years ago, but without the moderating influence of plate tectonics and the carbonate-silicate cycle, it lost that water and spiraled into the hellscape it is today. Mars, meanwhile, is too small for plate tectonics. Plate tectonics requires a planet with sufficient internal heat to drive mantle convection, which in turn drives the movement of the surface plates. Mars, with only about 11% of Earth's mass, cooled too rapidly in its history and its lithosphere froze into a single, thick, immobile plate. Without the recycling of carbon, volcanic outgassing gradually became the dominant process, but Mars also lacked the gravity and magnetic field to retain the atmosphere that the volcanoes produced. The result is a thin, carbon dioxide-dominated atmosphere too thin to trap much heat, leaving the surface cold and dry. Earth's size, roughly twice Mars's diameter and 10 times its mass, was also important for plate tectonics. The larger mass means Earth retains more internal heat from both its initial accretion and from the ongoing decay of radioactive isotopes in its interior. This heat drives the mantle convection that moves the plates. Research published in 2022 in the journal Nature Communications suggested that the probability of a planet having plate tectonics may be as low as 0.003%, meaning that only about 3 in every 100,000 planets might have the right combination of size, composition, water content, and internal heat to sustain active plate tectonics. If this estimate is even approximately correct, it means that Earth's plate tectonics is one of the rarest features in the universe and one of the most important for the sustenance of complex life. Earth's magnetic field is another feature that distinguishes our planet from its rocky neighbours and from the vast majority of rocky planets in the known universe. Earth's magnetic field is generated by a process called the geodynamo. In Earth's interior, the outer core consists of liquid iron and nickel, surrounding a solid inner core. As Earth rotates, the liquid outer core convects, meaning that hotter material rises and cooler material sinks in complex patterns. The combination of this convection with Earth's rotation generates electrical currents in the conductive liquid iron, and these currents generate a magnetic field that extends from the interior of the Earth out into space, forming the magnetosphere. The magnetosphere is an invisible but crucial shield. When charged particles from the Sun, in the form of the solar wind and occasional massive ejections called coronal mass ejections, stream toward Earth, they encounter the magnetosphere. The magnetic field deflects most of these particles around the planet, causing them to flow around the magnetosphere rather than hitting the atmosphere directly. Some particles are funneled toward the polar regions, where they interact with the upper atmosphere to produce the aurora borealis and aurora australis, the northern and southern lights, which are the visible evidence of the magnetosphere doing its protective work. Without this shield, the solar wind would gradually strip away Earth's atmosphere over geological timescales, just as it did to Mars. Mars lost its global magnetic field approximately 4 billion years ago. Scientists believe that Mars's small size meant it cooled faster than Earth, its liquid core solidified, and the geodynamo shut down. Once the magnetic shield was gone, the solar wind began stripping away Mars's atmosphere. Over billions of years, Mars went from having a potentially thicker atmosphere and possibly surface water to having the thin atmosphere and dry cold surface it has today. The stripping of Mars's atmosphere by the solar wind is not a theoretical prediction. NASA's MAVEN mission, which has been studying Mars's atmosphere from orbit since 2014, has directly measured the rate at which charged particles from the Sun are stripping ions from Mars's upper atmosphere and carrying them away into space. MAVEN has measured that the solar wind strips away roughly 100 grams of atmosphere from Mars per second, which over billions of years adds up to an enormous loss. Venus presents a different case. Venus has no significant global magnetic field, yet it retains a thick atmosphere. The reason is that Venus's atmosphere is so thick and its upper atmospheric winds so strong that the interaction with the solar wind occurs high above the surface, and the dense lower atmosphere is protected by the sheer mass of gas above it. But the absence of a magnetic field on Venus is one of the reasons scientists believe Venus cannot support life. Without a magnetosphere, the surface and any organisms on it would be exposed to cosmic radiation at levels far higher than Earth. And the combination of the runaway greenhouse effect and the absence of a magnetic field means Venus has effectively lost any water it may once have had, as the solar wind broke apart water molecules in the upper atmosphere and carried the hydrogen away. Earth's magnetic field has also undergone reversals throughout its history, events in which the north and south magnetic poles switch places. These reversals happen irregularly, roughly every 200 to 300,000 years on average, though the intervals vary enormously. During a reversal, the magnetic field does not vanish instantaneously. It weakens, becomes complex and disorganized, with multiple magnetic poles appearing at various latitudes, and then gradually reorganizes with the poles reversed. The entire process may take thousands of years. During this transitional period, the magnetic shielding of Earth is reduced. Evidence from the geological record suggests that these reversals do not cause mass extinctions, which implies that life can survive periods of weakened magnetic shielding, perhaps because the ozone layer provides additional protection from solar ultraviolet radiation, and because the remaining magnetic field, though weak and disorganized, still provides some deflection of the most energetic particles. The last full reversal was approximately 780,000 years ago, known as the Brunhers-Matuyama reversal. Some scientists have noted that the magnetic field has been weakening over the past few centuries, which has generated speculation about whether a reversal may be coming. But the scientific consensus is that this does not represent an immediate threat to life on Earth. Water. the substance that covers 71% of Earth's surface, the medium in which life almost certainly originated, the solvent that enables the chemical reactions of metabolism, the most studied molecule in biochemistry, and yet, in many ways, still one of the most mysterious. How did Earth get its water? And why does Earth have exactly the right amount of it? The origin of Earth's water is one of the great questions of planetary science, and the scientific community has been refining its answer for decades. The prevailing view for most of the 20th century was that water was delivered to Earth primarily by comets, icy bodies from the outer solar system that impacted the inner planets during the late heavy bombardment. But this view has been complicated by isotopic evidence. Water molecules contain oxygen and hydrogen atoms, and hydrogen exists in two forms: ordinary hydrogen with one proton in the nucleus, and deuterium, sometimes called heavy hydrogen, with one proton and one neutron. The ratio of deuterium to ordinary hydrogen in a water sample is a chemical fingerprint that reflects the conditions under which it formed. When scientists measured the deuterium to hydrogen ratio in comets from the Oort cloud, like Halley's Comet, they found that the ratio was roughly twice that of Earth's ocean water. If comets had delivered most of Earth's water, the ratios should match. They do not. The current best understanding is that Earth's water came primarily from a class of asteroids called carbonaceous chondrites, specifically C-type asteroids from the outer asteroid belt, which have deuterium to hydrogen ratios much closer to that of Earth's oceans. Measurements of water in meteorites from C-type asteroids have confirmed this match. This means that Jupiter's role in Earth's water story is more complex and more interesting than simple protection. In the early solar system, Jupiter's gravity stirred the outer asteroid belt, sending water-rich C-type asteroids on orbits that brought them into the inner solar system, where they impacted the young Earth and delivered the water that would eventually become the oceans. Simultaneously, Jupiter was deflecting many more dangerous large bodies away from the inner system. Jupiter was, in a sense, both the delivery driver and the security guard, selectively allowing water-bearing small bodies in while deflecting the most dangerous large impactors. A third contribution to Earth's water may have come from the process of volcanic outgassing. The material from which Earth formed contained hydrated minerals that have water molecules chemically bound within their crystal structure. As this material was melted and churned in the early molten Earth, water was released as steam from volcanic activity and contributed to the nascent atmosphere, and as the planet cooled, condensed to form liquid water on the surface. The relative contributions of C-type asteroid delivery, cometary delivery, and volcanic outgassing remain an active area of research, but the current consensus favours C-type asteroids as the dominant source. What is equally important and often overlooked is not just how Earth got its water, but why it retained the right amount. Earth's water constitutes about 0.023% of Earth's total mass, which is an extraordinarily small fraction. But that small fraction, about 4 billion cubic kilometers of water, is just enough to cover most of Earth's surface to the depth we observe while leaving continental land masses above the waterline. This balance between ocean and continent is itself significant for habitability. Continents provide the silicate rock surfaces that participate in the carbonate-silicate weathering cycle. They provide diverse habitats from mountain to forest to coastal wetland. They provided the tidal pool environments where some scientists believe life first emerged onto land. A planet entirely covered by a global ocean would have no silicate weathering on land and no terrestrial habitats for complex land-based life. A planet with insufficient water to have significant oceans would miss the enormous benefits that oceans provide for climate regulation, nutrient cycling, and biological diversity. Earth has the right amount of water to have both extensive oceans and extensive continents, a balance that seems to be important for sustaining a biosphere of maximal complexity and resilience. The carbonate-silicate cycle, already discussed in the context of plate tectonics, also directly involves the ocean. Carbon dioxide dissolved in the ocean participates in the chemistry that builds carbonate shells in marine organisms, from tiny foraminifera to clams and corals. When these organisms die, their shells sink to the seafloor and accumulate as carbonate sediment. This biological pump for removing carbon from the atmosphere and storing it in marine sediment is an enormously important component of Earth's carbon cycle and its climate regulation system. The evolution of shell-building organisms, which happened during and after the Cambrian explosion, approximately 541 million years ago, dramatically enhanced the efficiency of this biological carbon pump and may have contributed to the cooling trend that characterized the subsequent geological eras. Life did not merely adapt to Earth's climate. It actively modified Earth's climate, creating feedback loops that both stabilized and destabilized the climate on different timescales, in ways that ultimately allowed for the extraordinary diversity of environments that exist today. Let us now zoom out from Earth and look at the broader picture of what we know about other planetary systems. Because the contrast between our solar system and the systems we have discovered around other stars is one of the most compelling pieces of evidence for the extraordinary nature of our cosmic address. As of 2025, astronomers have confirmed more than 5,600 exoplanets, with thousands more candidate planets awaiting confirmation. This represents an enormous dataset about the diversity of planetary systems in our galaxy. The Kepler Space Telescope, which monitored roughly 150,000 stars for the 4 years of its primary mission before a mechanical failure in 2013 ended its planet-finding capability, confirmed the existence of 2,662 exoplanets. The TESS mission, the Transiting Exoplanet Survey satellite launched in 2018, has been extending the survey to brighter and closer stars, identifying thousands more exoplanet candidates. Together, these missions have given us an unprecedented statistical picture of what planetary systems actually look like. The picture is striking. The most common type of planet in the known exoplanet population is the super-Earth or mini-Neptune, a planet with a mass roughly 2 to 10 times Earth's mass, with a size roughly 1.2 to 4 times Earth's radius. These planets do not exist in our solar system. We have nothing between the mass of Earth and the mass of Neptune's 17 Earth massae. The gap between Earth's size and Neptune's size in our solar system is completely devoid of planets, yet this size range is the most common in the galaxy. The absence of a super-Earth in our solar system is not a trivial detail. It is one of the features that makes our solar system unusual. Super-Earths and mini-Neptunes are relevant to the habitability question for several reasons. If a super-Earth is rocky, it might have higher gravity, potentially thicker atmosphere, and potentially different geological dynamics than Earth. If it is a mini-Neptune, it likely has a thick hydrogen-helium envelope around a rocky or icy core, making its surface conditions very different from Earth's, and probably hostile to life as we know it. The nature of the transition between these categories is itself a hot topic of current research. Observations from the Kepler mission revealed what scientists call the radius gap, a relatively empty band in the distribution of planet sizes at around 1.5 to 2.0 Earth radii, below which planets tend to be rocky and above which they tend to be gaseous. This gap is thought to result from atmospheric escape driven by stellar radiation stripping the atmospheres from the smaller planets in this range. Among the most famous and intensively studied exoplanet systems is TRAPPIST-1, a system located approximately 40 light-years from Earth. TRAPPIST-1 was announced with great fanfare in 2017, when NASA announced the discovery of 7 Earth-sized planets orbiting the TRAPPIST-1 star. 3 of these planets, TRAPPIST-1, F and G, lie within the habitable zone of the star. The announcement generated enormous excitement about the prospect of life on these worlds. But as we have learnt more about the TRAPPIST-1 system, particularly through observations with the James Webb Space Telescope, the picture has become considerably more sobering. TRAPPIST-1 is a red dwarf star, with only about 8% of the mass of our Sun and about 0.05% of the Sun's luminosity. Because the star is so dim, all 7 TRAPPIST-1 planets orbit extraordinarily close to it. TRAPPIST-1b, the innermost, orbits at only 0.0 m1 AU, which is about 50 times closer to its star than Mercury is to our Sun. Even TRAPPIST-1G, the outermost of the 7, orbits at only 0.028 AU. By comparison, Mercury orbits at 0.39 AU. All 7 TRAPPIST-1 planets are crammed into an orbital region that would fit comfortably inside Mercury's orbit around our Sun. The JUICed observations of TRAPPIST-1 have yielded results that have dampened the initial optimism. JUICed observed TRAPPIST-1b and TRAPPIST-1c, the 2 innermost planets, and found that they appear to have no significant atmospheres. The measurements showed that their dayside temperatures were consistent with bare rocky surfaces without atmospheric circulation, meaning no atmosphere was present to distribute heat from the dayside to the night side. TRAPPIST-1d, the first of the potentially habitable zone planets, was also observed, and the results revealed only a very thin atmosphere at most, far less than would be needed to support surface liquid water. TRAPPIST-1 was observed by JWST in studies reported in 2025, and while the results were not as conclusive as for the inner planets, the indications were not strongly positive for a substantial Earth-like atmosphere. The picture that is emerging from the JEST data is that TRAPPIST-1, despite its initially exciting properties, hosts planets that are likely barren, airless rocks rather than Earth-like worlds with oceans and potential for life. The likely reason is the intense stellar flare activity of the red dwarf and the tidal locking of the planets. Kepler 442b is another frequently cited candidate for an Earth-like exoplanet. It is a planet with a radius of about 1.34 times Earth's, orbiting within the habitable zone of an orange dwarf star approximately 1,200 light-years away. Its equilibrium temperature is estimated to be around -2.6 degrees Celsius, making it quite cool, but potentially habitable if it has a sufficient greenhouse effect. The star it orbits, Kepler 442, is a K-type star, somewhat cooler and less luminous than the Sun, but more stable than a red dwarf. Kepler 442b is often listed as one of the most Earth-like known exoplanets, but critical limitations in what we know about it must be acknowledged. We know its size from the Kepler transit observations. We do not know its mass, its atmospheric composition, whether it has liquid water, whether it has a magnetic field, whether it has a moon, whether there is a Jupiter-equivalent gas giant Guardian in the same system, or any of the other specific parameters that we have been discussing as critical for habitability. It is Earth-like in size and in its orbital distance from a somewhat Sun-like star. Beyond that, we know very little. The honest scientific assessment is that of the thousands of exoplanets we have discovered, we have yet to find a single one that is confirmed to have the full suite of properties that make Earth habitable. We have not found a planet that is confirmed to have liquid water, a substantial oxygen-rich atmosphere, active plate tectonics, a large stabilizing moon, a magnetosphere comparable to Earth's, and a Jupiter-equivalent guardian planet in the outer system. This does not mean such planets do not exist. The vast majority of exoplanets we have discovered are detected by indirect methods, primarily the transit method, which detects the tiny dimming of a star's light when a planet passes in front of it, and the radial velocity method, which detects the tiny wobble a planet induces in its star's motion. These methods are enormously biased toward detecting large planets in close orbits. Small, Earth-sized planets in wide orbits around Sun-like stars are at the very edge of current detection capabilities. Our statistical sample is dominated by easy-to-detect planets and is not representative of the full population. This observational bias is crucial to keep in mind when evaluating how unusual our solar system is. When astronomers say that most discovered planetary systems have hot Jupiters or compact super-Earth systems, they are making a statement about what Kepler and TESS found among the relatively easy-to-detect planets. It is not yet clear what the full distribution of solar system architectures looks like when you include the harder-to-detect Earth-sized planets in wider orbits. A 2023 study using the SPHERE instrument on the Very Large Telescope in Chile suggested that when looking at wide-orbit gas giants detectable by direct imaging, solar systems with a configuration similar to ours may be more common than the Kepler statistics suggest. But even if our architecture is not vanishingly rare, the question is not just about the architecture. It is about the full ensemble of properties, and for that full ensemble, we have no confirmed counterpart. In the year 2000, paleontologist Peter Ward and astronomer Joe Brownlee published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. In it, they argued that the conditions that allowed complex multicellular life to evolve on Earth are so specific and so dependent on such an unusual combination of factors that complex life is likely extraordinarily rare in the universe. Their argument was not about the rarity of life itself, which they acknowledged might be common in the form of simple microbes. Their argument was about the rarity of the conditions needed for the evolution of complex, multicellular organisms. They identified many of the same factors we have been discussing: the right type of star, the right location in the galaxy, the right planetary architecture with a Jupiter-equivalent guardian, the right size and composition of the home planet, active plate tectonics, a large stabilizing moon, a protective magnetic field, and sufficient geological time for evolution to operate. The rare Earth hypothesis has been both praised and criticized since its publication. Critics have pointed out that Ward and Brownlee may have been guilty of describing a solution, meaning life as we know it, and then identifying all the conditions that led to that specific solution, creating a kind of selection bias. They argue that life might be possible under a much broader range of conditions than Ward and Brownlee assumed, including life based on different biochemistry in environments very different from Earth's oceans. This counter-argument is valid and important. We have only one example of life in the universe, life on Earth, and extrapolating from that single example to conclude that all life everywhere must require the same specific conditions is scientifically questionable. The universe may have invented life in ways we have not yet imagined, using chemical systems that do not require liquid water, carbon-based chemistry, or any of the other features we consider essential. However, the rare Earth argument has not been refuted. The discoveries of the Kepler and TESS missions have in some respects supported it, by showing that solar systems with our architecture are uncommon. The JWEST observations of the TRAPPIST-1 system, which showed those planets to likely have lost their atmospheres to their active red dwarf, supported the concern that red dwarf systems may not be hospitable to life. And the continued absence of any detected biosignatures in exoplanet atmospheres, despite the increasing sensitivity of our instruments, is at least consistent with the idea that Earth-like habitable worlds are not common. The counterpoint to rare Earth is the mediocrity principle, also known as the Copernican principle, which holds that Earth should be assumed to be a typical planet rather than an exceptional one, and that the universe should be assumed to be full of life rather than exceptional in its hospitality to life at Earth. This principle has a distinguished history. Nicholas Copernicus displaced Earth from the center of the universe by demonstrating that Earth orbits the Sun, not the other way around. This was the first great act of cosmic humility in science, the recognition that we do not occupy a privileged position in the cosmos. Subsequent centuries of science have repeatedly confirmed this lesson. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. At every scale, the universe does not appear to be organized around us. The mediocrity principle extends this logic to suggest that life is not likely to be uniquely concentrated on Earth, but is probably common throughout the universe. Both the rare Earth hypothesis and the mediocrity principle are scientific positions, not certainties. The honest answer is that we do not yet have enough data to decisively favor one over the other. What we can say with confidence, based on the evidence we have, is that the specific combination of circumstances that created and maintains life on Earth involves an extraordinary number of factors, each of which was not inevitable, each of which required specific physical conditions to be in place, and each of which contributes to a system of overlapping protections, regulations, and enablers that together make Earth the extraordinary world it is. The timeline of life's development on Earth adds another layer to the argument for our solar system's extraordinary nature. Life on Earth appears to have originated with remarkable speed after the end of the Late Heavy Bombardment. The Late Heavy Bombardment, which lasted from approximately 4.1 to 3.8 billion years ago, was a period of intense asteroid and comet impacts that repeatedly sterilized the surface of the early Earth. The largest impacts during this period would have vaporized the oceans, filling the atmosphere with superheated steam for periods of years to decades, making the surface completely inhospitable to life. Yet within approximately 100 million years of the end of this bombardment, we have evidence of life. The oldest confirmed microfossils, stromatolites formed by microbial mats, have been found in rocks in Western Australia dating to approximately 3.48 billion years ago. Even older potential evidence of microbial life, in the form of carbon isotope signatures consistent with biological activity, has been found in rocks dating to approximately 3.7 billion years ago in Greenland. Some researchers have reported even older potential chemical traces of life, though these are more controversial. The speed of life's origin is significant. It suggests that once the conditions for life were in place, the emergence of living chemistry was not a vanishingly improbable event that required hundreds of millions of years of random chemistry. It happened relatively quickly. This is consistent with the idea that life's emergence may be a natural consequence of chemistry under the right conditions, rather than an astronomically unlikely accident. This is one of the main arguments against the rare earth position, the argument that life is common. But even if life in the form of simple microbes is common, the subsequent evolution from simple microbes to complex multicellular organisms is a much longer and more contingent process. After the first single-celled life appeared approximately 3.5 to 3.8 billion years ago, life remained essentially single-celled for approximately 2 billion years. This was not a period of stagnation. Evolution was proceeding, biochemistry was diversifying, new metabolic pathways were emerging. But there were no animals, no plants, no fungi, just an ocean full of microbes. Then, approximately 2.4 billion years ago, a transformative event occurred. Certain bacteria evolved the ability to split water molecules using sunlight and use the captured energy to fix carbon dioxide into organic molecules, releasing oxygen as a byproduct. This is oxygenic photosynthesis, and the organisms that invented it were the cyanobacteria. Over the following hundreds of millions of years, cyanobacteria multiplied and spread across Earth's oceans, pumping oxygen into the atmosphere in what is called the Great Oxygenation Event. The atmospheric oxygen concentration rose from essentially zero to levels detectable in the geological record by about 2.4 to 2.1 billion years ago. The Great Oxygenation Event was catastrophic for many of the existing anaerobic organisms, for which oxygen was a toxic waste product. But it was also one of the most consequential biological events in Earth's history, because oxygen is a high-energy molecule whose chemical reactions release far more energy than the fermentation and sulfur-based metabolisms available to earlier life. The availability of oxygen as an electron acceptor for cellular respiration enabled the evolution of cells that could extract much more energy from food, energy that could be invested in building and maintaining complex structures. Without the Great Oxygenation Event, the energy budget available to life would have been far too limited to build the complex multicellular organisms that eventually emerged. Multicellular life appeared in the fossil record approximately 600 million years ago in the form of the Ediacaran fauna, a collection of soft-bodied organisms that are the earliest known complex multicellular creatures. Then, approximately 541 million years ago, one of the most dramatic events in the history of life occurred. In a geologically brief period of only a few tens of millions of years, virtually all of the major animal body plans we know today appeared in the fossil record. This is the Cambrian explosion, and it represents the moment when evolution's toolkit expanded from microbial chemistry to the extraordinary diversity of complex animal life. The causes of the Cambrian explosion remain a topic of active scientific debate, with proposed contributing factors, including the rise of oxygen to levels sufficient for energetically demanding animal metabolisms. The evolution of predation as an ecological strategy driving an arms race of defensive innovations, changes in ocean chemistry, including the availability of calcium for shell building, and changes in Earth's climate and ocean circulation patterns. The subsequent history of life on Earth has been punctuated by 5 major mass extinction events. The Ordovician-Silurian extinction approximately 443 million years ago, the late Devonian extinction approximately 375 million years ago, the Permian-Triassic extinction approximately 252 million years ago, the most severe, killing roughly 96% of marine species and 70% of terrestrial vertebrate species, the Triassic-Jurassic extinction approximately 201 million years ago, and the Cretaceous-Paleogene extinction approximately 66 million years ago, which killed the non-avian dinosaurs. Each of these extinctions was caused by different factors including massive volcanic activity, climate change, and in the case of the Cretaceous-Paleogene extinction, a large asteroid or comet impact at the Chicxulub site in what is now the Yucatan Peninsula of Mexico. Each time, life recovered, often more diverse and complex than before, as surviving lineages diversified to fill the ecological niches left vacant by the extinctions. Life on Earth has been remarkably resilient, bouncing back from even the most catastrophic resets. The evolution of complex intelligence emerged from the mammalian lineage that diversified in the aftermath of the dinosaur extinction. The genus Homo appears in the fossil record approximately 2 to 3 million years ago, and anatomically modern Homo sapiens evolved in Africa approximately 300,000 years ago. The emergence of complex language, abstract thought, and technological civilization in Homo sapiens represents the most recent and perhaps most consequential event in this 4 billion year story. It is the event that made this conversation possible. The timing of this emergence within the Sun's life is worth pondering. The Sun is approximately 4.6 billion years old and will remain on the main sequence for another approximately 5 billion years. Humanity arrived at roughly the halfway point of the Sun's stable life. We did not arrive in the early, tumultuous era when the Sun was young and variable, and the late heavy bombardment was sterilizing the inner solar system. We did not arrive in the dying era when the Sun will begin to expand into a red giant, making Earth uninhabitable. We arrived at the cosmic version of a quiet Tuesday afternoon in the Sun's middle age, a period of extraordinary stability, in a solar system that has settled into a long-term stable orbital configuration, on a planet with a fully established atmosphere, biosphere and carbon cycle, with a moon that stabilizes our axial tilt and a Jupiter that guards our outer solar system. Now let us bring together the mathematical weight of all of this. The Drake equation, proposed by astronomer Frank Drake in 1961, is a framework for estimating the number of technologically advanced civilizations in the galaxy. It multiplies together a series of factors, including the rate of star formation, the fraction of stars with planets, the fraction of those planets in the habitable zone, the fraction where life actually emerges, the fraction where life becomes complex, the fraction where complex life develops technology, and the average lifetime of a technological civilization. The individual factors in the Drake equation are not all well constrained, but the equation provides a useful framework for thinking about the probability of our situation. If we take just a few of the factors we have discussed and try to assign rough probabilities, we get a sense of the cumulative rarity. The fraction of stars that are G-type, Sun-like stars, is about 6%. The fraction of G-type stars with a planetary system with a Jupiter equivalent in the right orbit, neither having migrated inward to destroy the inner system nor too close to perturb the habitable zone, is estimated by various researchers at perhaps 5 to 10%. The fraction of those systems where a rocky planet occupies the habitable zone at the right orbital distance is perhaps 5 to 20% based on Kepler statistics, though this remains uncertain. The fraction where that rocky planet has active plate tectonics is perhaps 0.003% based on the Universe Today article citing recent research. The fraction where it also has a large stabilizing moon is unknown but likely small, given that the Moon's formation required the extraordinarily specific Theia collision. The fraction where it also has a protective magnetosphere is uncertain, but likely less than half, given that Mars and Venus both lack meaningful magnetic fields. The fraction where it also has the right amount of water is uncertain. If you multiply even a conservative set of these probabilities together, you get numbers that suggest genuinely Earth-like planets are rare, perhaps very rare. But here is where intellectual honesty requires a careful pause. Multiplying probabilities in this way is only meaningful if the factors are independent, and they are not. The size of a planet affects whether it has plate tectonics, a magnetic field, and the ability to retain an atmosphere. All of these are interconnected. The presence of a large moon might be more common around planets in a certain size range. The position of a gas giant in the outer system affects both the delivery of water and the rate of impacts. These are not independent variables drawn from separate probability distributions. They are parts of an integrated planetary system where the factors influence and constrain each other. Additionally, there is the deep question of the anthropic principle. We can only be asking this question from a planet that has the properties necessary for our existence. The very fact that we are here asking about our planet's suitability introduces a selection effect that makes our planet appear more unusual from our perspective than it might be from a truly impartial cosmic view. Nevertheless, the convergence of evidence from exoplanet surveys, solar system science, planetary geology, and astrophysics tells a coherent and consistent story. Our solar system has features that are individually unusual and collectively rare, and those features work together in a way that created and maintains the extraordinary habitability of Earth. The Sun's stability, the position in the galactic habitable zone, the architecture of outer gas giants in the right positions, Earth's location precisely in the habitable zone, the nearly circular orbit, the well-tuned axial tilt, the Moon's stabilizing influence, the magnetosphere, the active plate tectonics, the carbonate-silicate cycle, the right amount of water, and the 4 billion-year geological timescale that allowed evolution to proceed from microbial origins to complex intelligent life. Every one of these things is real, well established by scientific evidence, and every one of them contributes to the answer to our central question. The James Webb Space Telescope, the most powerful space telescope ever built, launched on December 25, 2021, and began science operations in 2022, has been adding new chapters to this story with every year of operation. By 2024 and 2025, JWEST has revolutionized our ability to characterize the atmospheres of exoplanets, particularly smaller planets that were completely beyond the capabilities of previous instruments. The results have been sobering and illuminating in equal measure. As mentioned, the TRAPPIST-1 planets have shown little to no evidence of substantial atmospheres in several cases. The planet K2-18b, a mini-Neptune orbiting a red dwarf star in the habitable zone, was observed by JWST, and the initial analysis in 2023 suggested a possible detection of dimethyl sulfide, a molecule that on Earth is produced only by living organisms. This generated enormous excitement about the possibility of life on K2-18b. But the scientific community was appropriately cautious, and subsequent analysis has complicated the picture. K2-18b is likely a mini-Neptune with a deep hydrogen-helium atmosphere overlying a water-rich interior, not an Earth-like rocky world. The potential dimethyl sulfide detection remains controversial and unconfirmed, and even if confirmed, its presence in a non-Earth-like environment would not necessarily imply life. JWEST has also been making discoveries far beyond individual exoplanet atmospheres. It has detected carbon dioxide in the atmosphere of an exoplanet for the first time. It has studied the atmospheric composition of giant exoplanets in detail previously impossible. It has observed exoplanet weather patterns and thermal structures. Each of these discoveries adds to our understanding of the range of planetary conditions in the universe and helps contextualize the specificity of Earth's conditions. As the mission continues, JWEST is working toward one of its primary goals, the detection of potential biosignatures in the atmospheres of rocky exoplanets in habitable zones. The key biosignature combination that astrobiologists look for is the simultaneous presence of oxygen and methane, which in the absence of a geological explanation would strongly imply a biological source, since these two gases react with each other and would normally not coexist without ongoing replenishment. As of 2025, no such biosignature detection has been confirmed for any exoplanet. Looking ahead, several missions are in development that will extend this search. The Nancy Grace Roman Space Telescope, developed by NASA, will conduct wide-field surveys that could discover thousands more exoplanets and better constrain the statistics of planetary system architectures. The proposed LIFE mission, a European concept for a space interferometer designed to directly image and characterize the atmospheres of nearby Earth like exoplanets, could transform our ability to search for biosignatures. The Habitable Worlds Observatory, a NASA concept for a next-generation ultraviolet and optical space telescope, is designed to directly image Earth-like planets and search for biosignatures in their atmospheres. These future missions represent humanity's deepening commitment to answering the question of whether we are alone, a question that is inseparable from the question of whether our solar system is truly unusual. There is a profound philosophical dimension to everything we have been discussing, one that connects the scientific facts to deeper questions about meaning, purpose, and our place in the cosmos. The question of whether our solar system is perfect is not just a scientific question. It is also a question about the nature of the universe and our relationship to it. There are two broad ways to interpret the extraordinary suitability of our solar system for life. The first interpretation is the one that Ward and Brownlee represent, and that the rare Earth hypothesis embodies. Our solar system is special, unusual, perhaps even unique in the universe, in the degree to which it combines the necessary factors for complex life. Under this interpretation, we are extraordinarily lucky, and the silence of the cosmos, the absence of detected signals from other intelligent civilizations despite decades of searching in the SETI program, Search for Extraterrestrial Intelligence, is at least partially explained by the rarity of the conditions that produce civilizations capable of transmitting signals. This is one proposed resolution of the Fermi paradox, the observation by physicist Enrico Fermi that if intelligent life is common in the galaxy, we should expect to have some evidence of it by now, and we do not. The second interpretation is the Copernican one. Our solar system may seem special to us because we are here, but similar or even better solar systems must exist throughout the galaxy, and life is probably common. Under this interpretation, the failure to detect biosignatures or signals from other civilizations is a function of our limited technological reach and the vast distances of space, not an indication of cosmic loneliness. The Milky Way is 100,000 light-years across. We have only had radio technology capable of broadcasting detectable signals into space for about 100 years. The volume of space our radio signals have reached is a tiny sphere of 100 light-years radius, a minuscule fraction of the galaxy's volume. If another civilization is transmitting from 500 light-years away, their signals have not yet reached us. If they are 1,000 light-years away and were transmitting 500 years ago, we might only receive those signals in another 500 years. The argument from silence is much weaker than it might initially appear. Both interpretations are scientifically defensible, and the honest answer is that we simply do not yet know which is correct. But there is a third interpretation, less often discussed, that combines elements of both. Perhaps our solar system is not the most perfect solar system in terms of some absolute optimization criterion, but it is one among a small but real number of solar systems that have the right combination of factors for complex life. And the selection effect of us being here means we inevitably find ourselves in one of those rare examples. This is the anthropic principle in action. The universe does not need to be fine-tuned for life in general, for us to observe that our particular corner of it is extraordinarily well-suited to our existence. We can only observe a universe that permits observers. This brings us to the deepest and most important thing that all of this scientific evidence points toward. Whether our solar system is the single most perfect solar system ever, one of many such solar systems, or truly unique in the observable universe, the evidence unambiguously shows that it is an extraordinarily rare and precious configuration. The Sun's stability, the orbital architecture, Earth's position and size and composition, the Moon, the magnetic field, the plate tectonics, the water, the 4 billion year geological timescale, the galactic neighborhood, none of these are guaranteed. None of them are common. All of them work together, and the result of all of them working together is a world where the chemistry of life could emerge, where complex organisms could evolve, where intelligence could develop, and where that intelligence could eventually understand enough about the cosmos to ask the question with which we began. We began by asking whether we live in the most perfect solar system ever. After everything we have examined, here is what the science actually tells us. Our solar system is extraordinarily unusual in ways that matter profoundly for habitability. It has a rare, stable G-type star in the right location in the galaxy. It has a planetary architecture that preserved the inner rocky planets from destruction by inward migrating gas giants. It has Jupiter in exactly the right position to play its complex role of gravitational gatekeeper. It has Earth positioned at 1 AU with a near-circular orbit and a well-tuned axial tilt. It has a moon of extraordinary size that stabilizes Earth's obliquity and created the tidal environments that may have been crucial to life's origin. It has a geodynamo generating a protective magnetosphere. It has active plate tectonics that regulate Earth's climate through the carbonate-silicate cycle over geological timescales. It has the right amount of water to support oceans and continents simultaneously. And it has provided 4 billion years of stable conditions for evolution to produce, step by painstaking step, the extraordinary diversity and complexity of life we see today. Is it the most perfect solar system ever? We do not know enough about the full diversity of solar systems in the universe to make that claim definitively. But it is an extraordinarily capable solar system. It is a solar system that has done something that we have confirmed nowhere else in the universe. It has produced life. It has produced complex, multicellular life. It has produced intelligent, self-aware, technologically sophisticated life that can look back at the system that produced it and ask with genuine scientific rigor what makes this place so extraordinary. And the answer to that question, as we have seen in exhaustive detail, is almost everything. Carl Sagan, in his reflection on the pale blue dot, the famous photograph of Earth taken by the Voyager 1 spacecraft from beyond Neptune in 1990, wrote that there is nowhere else, at least in the near future, to which our species could migrate. Visit, yes, settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. The scientific journey we have taken through this conversation gives those words a new and deeper weight. Earth is not just where we make our stand because we have not yet built the technology to live elsewhere. Earth is where we make our stand because it is embedded in a solar system of extraordinary rarity and capability. A solar system that in all the immensity of the universe we have yet to find the equal of. Every parameter we have examined, from the Sun's spectral class and luminosity stability, to Jupiter's orbital radius, to Earth's axial tilt, to the Moon's size, to the geodynamo's convection currents, to the carbonate silicate cycle, to the ratio of deuterium to hydrogen in our oceans, all of these specific numbers tell the same story. We live in a place that is not just habitable, but is deeply, elaborately, multiply-suited to life and to the long-term evolution of complexity. The universe is 13.8 billion years old. It contains 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Most of those stars have planets. The volume of the observable universe is approximately 4x10 to the power of 80 cubic meters. By pure numbers, the sheer vastness of the cosmos makes it difficult to believe we are truly alone. And yet, despite decades of increasingly sensitive searches for radio signals from other civilizations, despite the launch of the most powerful space telescope in history, and its increasingly detailed studies of exoplanet atmospheres, we have so far found no confirmed evidence of life anywhere other than here. The silence of the cosmos is not yet broken. Every confirmed exoplanet we have studied in detail has revealed either conditions far more extreme than Earth's, or a lack of the atmospheric signatures we associate with life. The universe, in all its vastness, has so far revealed to us only one confirmed example of a solar system that works. One confirmed example of a planet with life, and one confirmed example of intelligent beings capable of asking cosmic questions. That example is us. That solar system is ours. And based on everything the evidence shows, it is something extraordinarily special. The sun will continue to warm Earth for approximately 5 more billion years. The moon will continue to stabilize our axial tilt for the foreseeable future. Jupiter will continue its gravitational guardianship. Plate tectonics will continue to regulate our climate. The carbonate-silicate cycle will continue to adjust atmospheric carbon dioxide in response to changes in solar luminosity. The magnetic field will continue to deflect the solar wind. The biosphere will continue to evolve and adapt. This solar system, this improbable, extraordinary, rare, and precious configuration of matter and gravity and chemistry will go on doing what it has been doing for 4.6 billion years. Providing, sheltering, enabling, creating the conditions for the continuation of the only story we know, the story of life in the cosmos. The question we started with, do we live in the most perfect solar system ever, turns out to be the wrong question. Not because the answer is no, but because the question of perfection implies an external standard of comparison we do not yet have. What the evidence absolutely and unambiguously shows is something far more astonishing and far more humbling. We live in a solar system that is working in the deepest possible sense, working to maintain life over geological timescales, working to protect that life from the violence of the cosmos, working to regulate climate, recycle carbon, deliver water, shield from radiation, and provide the stability that 4 billion years of evolution require. And in a universe that, for all its vastness, has so far shown us nothing else that is working in this way, that fact is the most extraordinary fact in all of science. We are here, against all odds, in a cosmos of fire and void and radiation. We are here, on this particular rocky planet, around this particular stable star, in this particular well-positioned solar system, in this particular quiet arm of this particular spiral galaxy. At this particular calm moment in cosmic history, we are here. And the universe, in all its indifferent silence, has given us something it has given nowhere else we have yet looked. The capacity to look back. That is not a small thing. That is everything. End